Hi, welcome to Concept Based. I'm John Hepworth, and this is another Year 11 advanced topic. We're doing trigonometry of measures of angles. There's a specific part in your syllabus that's the heading has trigonometry with angles of any magnitude. And you can see this question that's being asked here is certainly one of those. The angles are of any magnitude from negative 120 degrees for one of them up to 585 degrees. So they're not limited to anything. So we're trying to work out, what's going on when we go out to these large angles. It's always particularly interesting once we go beyond that 360 degree angle, because it's like, well, haven't we gone around in a circle? Why are we going even further? What does this even mean? So that's something we want to have a look at today. For such a small question, there's two very distinct paths we can look at here for this question. One could be use your calculator. Calculators these days will answer in exact values, so you can just whack it in your calculator and answer it. But what it doesn't do by doing that is it doesn't give you a really clear picture of what's going on in terms of trigonometric functions. It doesn't set you up to really draw links between what I'm going to introduce as the unit circle and graphs and triangles. And I really do think that having a really good understanding of trigonometry requires you to be able to link all of those three together. So today, I'm not going to use the straight up calculator approach. I'm going to use a slightly different approach that's going to be certainly far more extensive, but hopefully give you a better understanding of what's going on in these large angles. As you could imagine, the calculator gives you no understanding. You type it in, press equals, and a magic number comes out, and you just trust that that is the true answer. Where we don't want to be doing that. We want to be working something out. Now, something I want to note here in your syllabus, it goes on about creating a circle with radius r. That's not typically what we do when typically we're looking at angles of any magnitude. We really want to create a circle of unit radius. It just takes away one complexity of the radius being any given size. We can look at that and change that in the future. Multiplying the radius out just simply makes the magnitude of the solution bigger by the multiple of r. So if the radius was twice as big, then our answer, say it was a third, will be 2/3. It just multiplies the answer out. So it's quite simple. But rather than thinking of it as it could be anything, and thinking of it as, no, let's just focus on the unit circle to get a definition of these angles, I think is a little bit easier. So let's have a little look at what a unit circle would look like. So if we're just in a Cartesian plane and we draw a unit circle, this means we're going out to 1 on each of the axes and down to -1. And I want to note here that over here we're on an x-axis and over here we are on a y-axis. So the syllabus talks about an angle being between a ray and the x-axis. So I'm going to draw a ray out on this circle here. And the angle we're talking about is the one just here, the angle between the x-axis and this ray. So essentially 0 starts at the x-axis. We then move anti-clockwise away from the x-axis and go around the circle for positive angles. Now, if you're the sort of student who's like, why? Why do we do that? Why do we start with north at 0, but we start with the x-axis at 0? Sometimes it is just in the forms of definition. But what I like to consider here is that additionally, initially we consider a number line, the number line being the x-axis, and we look at the positive side of it. Then we move towards the positive side of the y-axis, so we can talk about that being the origin of where these angles would begin from, moving in the positive direction off the x-axis toward the y-axis. There's a range of reasons we can give for that, but that's the one that I like to just give a simple basic explanation. Look, let's start on the number line, then change to 2 dimensions, Cartesian plane, and we have to go into the positive direction first, so that's going to be anti-clockwise. Okay. So we're in this section of the unit circle. This section is called the first quadrant. Therefore, obviously, this is going to be second because we're moving anti-clockwise. This is third, and this is fourth. Now, what we want to consider is what's happening for the trig ratios in those quadrants. And the only way we can consider those trig ratios is to look at a triangle. So if we actually turn this angle into a triangle here, I'm just going to color it in a little bit thicker. And I might even zoom in on it a little bit. Oh, no, it won't. So with that being the case, we now have sides of the triangle with our given angle theta. So this side of the triangle on the bottom here is a length x. Now, x is obviously going to change. As the angle gets bigger, that side length of that triangle will be different. And this over here is in the y direction. That's our y value of this triangle. And I said that this triangle's radius is unit. So therefore, this hypotenuse that we have here is a unit length, so it's 1. So we want to sort of take into consideration what trig ratios are we going to get out of this triangle if we've got x here, y here, theta here, and a hypotenuse of 1. Well, sine of theta is going to equal opposite, which is in this case y, over hypotenuse, which is 1. So y over 1. Cos theta is going to be the adjacent over hypotenuse, so that will be x over 1. And tan theta is going to be opposite over adjacent, so y over x. And so we need to commit that sort of concept of how that happens into our memory of what's going on here, so that we know when we think about our trig ratios and what quadrant we're in, depending on what size the angle is, whether or not the trig ratio will actually be positive or negative. So for example, let's look at cos theta equals x. If cos theta is in this first quadrant, then we are talking about an x component here. But if we took this angle and drew it out over here, well, now the x component that we start considering is this bit over here, and that actually would be negative. So cos in the second quadrant is going to be negative. In the third quadrant, it would be down here, and we're still talking about these x values over here, so cos would be negative again. But in the fourth quadrant, we're then talking about angles down here, and the x component would then be once again this positive part of this x component. So whether cos is positive or negative is just dependent upon whether x is positive or negative in the triangle that we're talking about when we give a given angle of any magnitude. And obviously the angle of magnitudes change at multiples of 90, 180, 270, and back around to 360 or 0 degrees over here. All right, so what we now want to do is we want to now think, well, how would we go and do something of sine negative 120? Okay, so let's go back to this. Where's this angle going to be? Negative 120 degrees. Well, we said that the angles are positive anti-clockwise like that. So we have to go backwards like this to go negative, and we're going to go negative 120 degrees. So obviously once we get to here, we would be at negative 90 degrees. And so then we keep going and we end up over here, right? At some angle here where this would be negative 120 degrees. Now we're asked for the sine component. Now we worked out before that the sine component is asking us, well, how big is the y section of our triangle? Now you might say we haven't drawn a triangle. We have. We're always drawing the triangle in the quadrant that we're in. That's where we're getting our ratio from, because you can see that this point is creating a y value in this triangle of this size, and that's what we defined as being sine theta is the y value. Now we can definitely see over here that the y value is negative because it's going down below the origin, down below the x-axis. So we have some negative y value. The question is how big is this negative y value without using our calculator? What do we expect it to be? Well, the way we can work that out, what I teach it as, is you can work it out using a butterfly. And so the butterfly that I talk about is this. When you have negative 120 degrees, if you want to work in this triangle over here in the third quadrant, the theta that you would need to consider is this one here. And that's an acute angle. Now that acute angle there that creates this y angle, y size, is actually the same as the acute angle over here, because it would create this same y size. So this y side is equal to this y side over here. The only thing that's different is the one over in the third quadrant is negative, but the one in the first quadrant is positive. So this angle in the first quadrant is considered the primary angle. So we can just work everything out using acute angles, and then we just have to decide whether it's positive or negative depending on the quadrant that it's in. So what is the acute angle in this case? Well, if 120 degrees goes around the bottom here, the bit that we're missing in there is 60 degrees. So we'll be considering this 60-degree angle in the first quadrant to try and get our solution. So 60 degrees in here. Okay, so now we have to go and consider, well, what is sine of 60 degrees? And again, you may feel like, well, why are we delaying picking up the calculator? Aren't I just going to go and pick up the calculator now? No. Typically, when they ask you an exact value of an angle, it's going to be either a multiple of 30 or 60, well, which is really a multiple of 30, or 45 degrees or 90, because we have exact values for those. So in this one, we're talking about 60. So we draw our exact value equilateral triangle again. We get our 60-degree angle. We take our triangle, we chop it in half. We side length of 2 and 1, and we therefore remember that this is root 3. Or we look it up in the formula sheet, but I prefer that you practice doing this all the time so you don't have to look it up in the end. Now, sine is opposite over hypotenuse. So for this, sine 60 is equal to root 3 over 2. So that gives us that part, that primary angle part. But we need to come back here and go, hang on a second. The y value in this third quadrant is negative. So therefore, the sine of negative 120 is the same as sine of 60 degrees, except it's negative, and we get negative root 3 on 2. And that's how you get an exact value of angle of any magnitude. Now, the next one is better in terms of any magnitude because, again, it goes over that 360 and it makes us think a little bit more of what do we mean by any magnitude. So now it's asking us for tan 585 degrees. Okay, so the first thing we know we have to do is we have to go around 360 degrees. So we do a full revolution in the positive direction and we get back to where we started. Then we need to think, well, how much more do we need to now do? We now need to do another 225 degrees. Okay, so 225 degrees, we then need to go and get another 180. So 180 on top of our 360 gives us 540. And then we need another 45. So then we're coming again into this quadrant here to get our 45-degree angle. And now our primary angle is not 60 from the last question, it's 45 degrees. So now we would do tan of 585 degrees is the same as tan 45 degrees. However, we need to consider, is it positive or negative? Well, let's look back up here. In tan is y over x. The y value in our third quadrant is negative, but the x value in our third quadrant is also negative. So the tan function in that area is a negative value over a negative value, opposite over hypotenuse, opposite over adjacent. A negative over a negative is positive, so it's actually going to be positive. So it's staying the same. So all we need to do is work out what tan 45 is. So tan 45, we do by our exact value triangles again. Our isosceles right triangle, side length 1, that's a bit long for a 1, isn't it? And we get the 45-degree angles in the corner. And we want tan, which is opposite over hypotenuse, so it's 1 over 1. So tan 45 equals 1. So tan 585 degrees shall also equal 1, even though it's in that third quadrant. Now, doing that every single time for all of these any magnitude questions is a lot. There are some shortcuts. So the shortcuts that you can do is you can work out on the basis of all of these definitions that we've given that all of the angles are positive in the first quadrant, that the sine angles are positive in the second quadrant, that the tan angles are positive in the third quadrant, and that the cos angles are positive in the fourth quadrant. But any other ratio in those quadrants are negative. So for example, cos in the second quadrant is negative. So you don't have to go through and work all that part out again. You can just remember ASTC. I was taught it as all stations to central. I've taught this on the central coast of New South Wales, so they said all stations to Cardiff to remember it. You may make up a relative train station to your area or use it as a different acronym, but it just gives you a quick realization of whether you're talking as a positive value or a negative value. And the second part is that butterfly I spoke about. How do we take something from one of the quadrants into the primary quadrant? Well, the angles that we're always dealing with are the acute angles towards the x-axis. So if we were to draw the same size angle in all of these quadrants, it would end up looking like this. So if I was to do tan of theta in the first quadrant, it would be the same as tan theta in the second, tan theta in the third, tan theta in the fourth. I would only need to care about whether there'd be parts that are positive and negative. And you can see by drawing this triangle, these triangles, it ends up looking a little bit like a butterfly to me. And so because it looks like a butterfly, I call it the butterfly angles, which is the primary angle that gets you back into that first quadrant and allows you to do the calculation. What you are not doing is you are not taking into consideration the angle in that part. You're always finding the angle next to the x-axis, and that will find out what the primary angle ratio is for you. So this concludes the second way of doing it. The first way of doing it is having an excellent calculator that does exact values for you, and just plugging it in, getting an answer. But doing this process, like I said at the start, it really starts to link together your unit circles, linking together with function graphs. So why this looks like this, right? It really helps you in terms of that, which then relates to some triangle. And if we can get these three things working together in your mind, then you are going to certainly be stronger at trigonometry than if you're just relying on a calculator.